The Trojan asteroids are small bodies in our solar system. They share an orbit with Jupiter. There's two swarms of them. One located 60 degrees ahead of Jupiter in its orbit, and the other swarm is located 60 degrees behind Jupiter in its orbit. And these Trojan asteroids are remnants from planetary formation. So sometimes we'll call them the fossils of solar system formation. Their near neighbors might have gone into forming the giant planets. And so these objects then became captured in their locations today. And so in that way, we can look and see what went into forming the planets in our solar system. The main goal of the Lucy mission is to explore the Trojan asteroids. We want to understand where these asteroids came from and why they're so diverse. And this is going to be our first ever exploration of these objects. From the Earth, we can see certain features on the Trojan asteroids. We can see where they're located, we can see their colors, and we can get spectra. Spectra can tell you about the surface composition. A spectrum is when you take light and spread it out into all its different wavelengths. And so you have the brightness of the light as a function of wavelength. So think of it like a rainbow, but you're going to divide up the colors even more finely than just Roy G. Biv. From Earth, the Trojan asteroids are just a point of light, and you can't tell one part of the Trojan asteroid composition versus another part. And Lucy is going to be able to get that detail close up. But we'll be able to do that by taking this spacecraft and these instruments to the Trojan asteroids, and we'll be able to see how the surface composition varies across the Trojan asteroids. Additionally, we have really large solar arrays because we are solar-powered spacecraft. The spacecraft gets its power from the sun. At the Trojan asteroids, we're more than 5 times further from the sun than Earth is, so there's much less light. We need large solar arrays to power our spacecraft. And in fact, we will be the furthest operating spacecraft powered by solar arrays during our mission.
Trojan asteroids are found in Lagrange points, which are these special places that lead or follow a planet in its orbit by 60 degrees. And it's sort of where the gravitational force of the planet and the gravitational force of the sun all cancel out. So if you put an object there, it will stay there for a long period of time, basically forever. So when we see objects there, these are objects that we know were in place a very long time ago. So if you just take a random asteroid and just put it in the outer solar system, the gravitational force of the 4 giant planets will just clear them out in a very short period of time. So they'll basically be gone. So the only places, it turns out, in the outer solar system where you can find stable regions are these Lagrange points. Lucy in particular is going to go after the Jupiter Trojans. We're trying to see a type of object that represents and constrains the formation of the outer planets. And you need to go to these Lagrange points in order to see that kind of object. One of the really groovy aspects of our mission is its trajectory, because we're visiting a record number of objects like these Trojans. And we do that with this very complicated dance, particularly in the beginning, where we are using the Earth actually as a gravitational slingshot. So Lucy will start off in an orbit very similar to the Earth, and then gravitational encounters with the Earth will actually pump it up so it gets out to the Lagrange points near Jupiter's orbit. So if you're going to understand how planets like the Earth formed, you have to understand how the bigger planets, which sort of dominated the whole process, came to be. And that's what Lucy is going to do.
The Lucy mission is a planetary mission to the Trojan asteroids that are around Jupiter. It's going to survey actually a total of 8 targets, 7 asteroids around Jupiter and 1 asteroid in the main asteroid belt. Once you know where you're going and the type of science that you want to take, one of the things that you start looking at is the spacecraft. What size spacecraft, where is it going, how much power does it need to carry, does it need solar arrays, what type of solar arrays, what type of vehicle is going to be used to launch it into space. So that dictates how much mass you can carry. And one of the things I do as a project manager is to assemble a team of scientists and engineers and technicians and business people to design that overall spacecraft to achieve your mission. In designing the spacecraft, you're always thinking about what type of environment is it going to be subjected to. Is it going to orbit around Earth? Is it going into deep space? Is it going to Mars? Is it going close to the sun? And so as engineers, one of the things that you're thinking about very early on is how can you design this system and test this system in order to verify and convince yourself that it's going to survive in space. And as part of that, it goes through a very rigorous test program. And so we call it shaking and baking. And so we actually put it through what we call a thermal vac chamber in which we simulate the space environment. We also put it on what we call a vibe table in which we vibrate it, so we shake it. And one of the important things that you have to do in order to be convinced that it's going to survive is to make sure that the environment in which you're testing it in, the simulated environment, is harsher than what it's going to see in space. So once you subject that spacecraft or that instrument to that environment, then you can have confidence that it's going to last the lifetime that it's been designed for.
So to steer a spacecraft from millions of miles away, we have to first track its trajectory. So we have to determine where in the solar system the spacecraft is, predict where it's heading, and compare that to where we want it to go. So the navigation team ensures Lucy's on the right trajectory by tracking Lucy's position and velocity in the solar system, predicting where it's headed, and adjusting its course so that it aces the flyby. So once Lucy starts approaching one of its asteroid targets, the navigation team utilizes the instruments, the cameras on board, to take pictures of the asteroid and background stars, and that helps us hone in on targeting this close flyby. So commands travel at the speed of light, and over the course of Lucy's trajectory, its position from Earth is varying substantially. When Lucy is near Earth during our Earth gravity assists, it takes a mere seconds for the data or commands to be received by the spacecraft and for the spacecraft to send data back to us. But at the farthest extent of Lucy's trajectory and the farthest distance from Earth, it can take up to an hour for our commands to be received traveling at the speed of light. It's not only the data encoded in the signals, but it's the properties of the signals itself. We know what time the spacecraft sent the data, and we know what time it was received on Earth. So we can calculate how long it took the signal to travel at the speed of light, and that gives us information about how far Lucy is from Earth. And then we also can get velocity information because the spacecraft is moving away from the Earth as it's sending those signals, and so there's a change in the frequency of the radio signal, and that gives us information about velocity. So like all NASA missions, Lucy is designed to be robust to anomalies or surprises. But in the event that something unexpected happens, there's either a contingency plan on the shelf or a group of relevant mission experts are brought in to come up with the best solution to solve the problem.
Hi, my name is Danya Douglas Bradshaw, and I'm the project manager for the Lucy project, which will be the first mission to the Trojan asteroids. Building a spacecraft is quite exciting. I worked many decades as a mechanical engineer, really focused on thermal and heat transfer. And so when you work in that capacity, you are supporting the development of spacecraft as well as instruments.
Hi, my name is Dr. Carly Howitt, and I'm the instrument scientist of the MVIC camera on Lucy. I love working on Lucy for so many reasons, but one of them is being able to explore the universe from the comfort of my own office. So I don't have to don diving gear or, go into these dangerous or hard situations. I get to enjoy the data as it comes back from the comfort of my office and explore the universe that way.